This is Ms. Miner. This is 9A. We're going to be in Unit 9 talking about what are called radicals and the real number system. First, let's just remind ourselves how to turn a number into a decimal number. That's going to be a skill that we're going to need for this unit. So remember, anytime I have a fraction like 2/5, this fraction bar, I gotta get going here this morning. This fraction bar that's in here is telling me the same thing as divide, right? So if I want to take 6 2/5 and turn it into a decimal number, well, the 6 is still going to be my ones place. And then I'm going to take 2 and divide it by 5. I'm just going to use my calculator to do that, and I'm going to get 0.4. So if I have a fraction, I can turn it into a decimal. Same thing here. The -3 is going to be my ones place. And then 2 divided by 6. When I put that in my calculator, what I get is 0.33333333. Well, we're going to use in this unit what's called a repeating bar, a repeater. I call it a repeater. If it has a repeater, if it has the line drawn on top, it's called a repeater. And so whatever that line is drawn over, that's what is repeating over and over again an infinite number of times. So let's say I had a number like 0.614 and the repeater was over the top of all of those things. Well, then what is repeating is the 614, 614, 614, and it's going to go on and repeat an infinite number of times. Okay. So anytime I have something that's repeating, I'm going to draw the bar over it to indicate that it's repeating on an infinite number of times. And you'll see me do that a lot during this unit. Okay, then we need to do, in this unit, we're going to be talking about radicals. See this weird check marky sign that looks like that? That's what we call a square root. And it is a radical. The square root is a radical, the cube root is a radical, and we're going to talk more about those as we go on in this unit. But we can get a good decimal approximation of what the square root is from our calculator. So depending on what calculator you have, you're going to use the square root to help you. And the square root is the opposite of the exponent of 2. So we're going to find out later on in this unit exactly what radicals are and how we use them. But for today, we're going to use the square root button on our calculator, whatever calculator you have, and we're going to put in the square root in order to get a decimal approximation. So if I put the square root of 15 in my calculator, and so you'll want to get a calculator that has a square root function on it, and you're going to put in square root of 15. And if I hit enter, I get the decimal approximation 3.87. And then I have a whole bunch of numbers, 8, 7, 2, 9, 8, 3, 3, 4, 6. And then normally my calculator will round off that number because it doesn't fit on the screen. This is a decimal that just keeps going on and on and on. It never stops. It never repeats. And so in your notes today, I'd like you to write down a good vocabulary word that you're going to need for this unit. And the vocabulary word is a non-terminating non-repeating decimal. Okay, that's the word, non-terminating, non-repeating decimal. But what it means is, non-terminating means it never stops. It goes on and on for infinity. And it never repeats. And you might be saying, well, Ms. Miner, this repeated right here. It had 2 3s that repeated right there. But I mean a repeating pattern. It has to repeat the same pattern over and over again. Like this one up here is a repeating pattern, 0.614, 0.614, 0.614. That's a repeating pattern. And so it never repeats a pattern. Now, I might have a couple of numbers in there that repeat, but it never repeats a pattern. Now, sometimes we have what are called non-terminating, non-repeating decimals, and they'll do something like this: 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. And you might be saying, well, Ms. Minor, that is a repeating pattern. But this is a decimal number that I can't turn into a fraction. And so if it's going on, right? And when I say it repeats a pattern, it has to be repeating the same group of numbers over and over and over again. So this is slowly increasing, right? And it is kind of repeating, but it's not repeating the same pattern over and over again. Like it would have to repeat 2, 2, 2, 2, 2, 2. So that's kind of what I'm talking about there. It's a little tricky, but be careful with that. It has to be repeating the same pattern over and over again. Okay. So sometimes you'll see me abbreviate non-terminating, non-repeating as NTNR, just because it's a short notation, right? A shortcut notation. I don't have to write out non-terminating, non-repeating all the time, because that can get a little tedious. So Ms. Minor will sometimes abbreviate that as NTNR, non-repeating, non-terminating. Okay, and that's a good vocabulary word to have. Here is another example of a non-terminating, non-repeating decimal, pi, and we've all memorized that it is that 3.14 is equal to or approximately equal to pi, and that's what we kind of use as pi. But remember, pi is actually a decimal that keeps going on forever and never stopping, and so it's actually equal to 3.14159265, and then it keeps going on forever. So if you see these little dots at the end, that means it's going to continue on and never stop. So sometimes you'll see a non-terminating, non-repeating decimal with these dots at the end, and that's to indicate that it keeps going on forever. Usually with a repeater, we won't put the dots at the end, we'll put the bar over the top. Even though it also goes on forever, the bar is indicating that it's repeating that pattern on forever. So we don't put the dots at the end of a repeater. Okay, so there's some things, how to convert into a decimal. We can use our calculator to help us. Let's talk about what we're doing today. That's just a reminder, refresher from before in your earlier years of school, how to turn numbers into decimals. But today, what we want to be able to do is classify and order rational and irrational numbers. And rational and irrational numbers come from what's called the real number system. That is the number system that we use in our world, in the United States, in our classroom. The real number system, it sounds made up, but it is not. Okay, it is the number system that we normally use. And we're going to kind of talk about today that number system. There are other number systems. The imaginary number system is a number system that you will use when you get into higher levels of math, higher grades of math. It is not made up. It also sounds made up, but it is not. When I end up with stuff like the square root of a negative number, the square root of -2, if I stick that in my calculator, it's going to give me an error. My calculator can't actually calculate it. We also use the little Greek letter I as an indicator of imaginary number system. And these are examples of things that I can't calculate using the real number system, but if I switch into the imaginary number system, then I can calculate the square root of -2 and 8i. And so it is another number system that we use, in higher levels of math, and you'll talk about that when you get to that point. We will not be using the imaginary number system in this class, but just as so you know, there are other number systems. Another example of a number system that we actually use and calculate with is what's called the binary number system. The binary number system is what we use to code computers. It's a number system of ones and zeros that we use to code computers. So that's another example of a number system you may or may not have heard of. But, we do have other number systems. In our class, we use the real number system. We're going to talk about how to classify and order numbers in the real number system today. Okay, the first thing that we have to know is what are rational versus irrational numbers? Well, rational numbers, if you think of what the word rational means, it means it kind of makes sense. It follows a orderly pattern, or the word rational, I'm just trying to think of a general, it's kind of reasonable. It kind of makes sense. It kind of follows a pattern. It stays orderly, kind of a logical sense. Well, irrational numbers are the opposite, right? They kind of don't really make sense to us, and they seem illogical, or they seem like they are not in an orderly pattern. Okay, so what does that mean in math? Well, here's the definition of the mathematics definition of an irrational number. It's a number, okay, or an amount, a quantity, that is not expressible as a ratio. Remember that word ratio. Oh, sorry, not ration, ratio. That word ratio is the same as the word fraction. They mean the same thing. It's a comparison of two numbers, right? Usually with ratio, we say like 2 to 1, but 2 to 1, right? A ratio of 2 to 1 is the same as saying a fraction 2 to 1. Fraction is also a comparison of two numbers. And so I could replace that word as fraction in the definition. And that might make a little bit more sense to me. It's not expressible as a fraction. So an irrational number is a number that's not expressible as a fraction. And it has an infinite and non-reoccurring expansion. Well, wait a minute. Infinite and non-reoccurring. What does that sound like? Well, that sounds like a non-terminating, non-repeating decimal number. And that is exactly the case. The square root of 15 and pi are both examples of a irrational number because they have this infinite and non-reoccurring decimal expansion. And also, we use the square root indicator because sometimes we can't express these numbers as fractions, so we just leave them as square roots. We say the square root of 15. And we actually do use the square root of 15 in our calculations because our decimal expansion is so big and so long, right? That instead we just calculate using the square root of 15. And I'll show you how we do that in later units. But for right now, we use the Greek letter pi to symbolize this big long decimal expansion because we don't have a fraction or another way to express this big long decimal expansion that goes on forever and ever and ever. So irrational numbers are numbers that can't be expressed as fractions. They are not fractions. And they have non-terminating, non-repeating decimal expansions. Okay, so let's talk about the real number system. Here's kind of just it's almost like it works like a family tree, okay? The real number system kind of works like a family tree. And we have different branches of our family tree. In this case, we have two different branches of our family tree. One branch is called the rational numbers. The other branch is called the irrational numbers. So almost like a family tree. We just talked about irrational numbers. Irrational numbers are non-terminating and non-repeating decimals. Okay. Any number that has a non-terminating, non-repeating decimal is an irrational number. And we just saw some examples of that. The square root of 15 is an example of that. The letter pi, or the number pi, is an example of that. Another example would be like the square root of 2 would be an example of that. And we'll do some examples in just a minute. Over here I have some numbers, and we'll try and classify those in just a minute. But those are some examples of irrational numbers. Any number that when I calculate it out, it comes out as a non-terminating, non-repeating decimal. And remember, the key here is it cannot be expressed as a fraction. No fractions. Okay, I can't make fractions out of these numbers. They're these decimals that I can't turn into a fraction. Okay, so let's talk about the real number system right now. The real number system, the real number system we are talking about, but let's talk about the rational numbers. Okay, the rational numbers are like the other branch of our family tree. And the rational numbers start out with our immediate family, if you will. Our immediate family are called the natural numbers. We also call these the counting numbers. And the counting numbers are just our regular counting numbers, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, as high as I can count. You know, they go on for a long, long ways. Like if I spent some time at it, I could probably count really high, but they're just our regular counting numbers. Natural numbers are just our regular counting numbers that I would count with. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, as high as I can count, okay? And our rational number system kind of flows with the way numbers have been created historically. And so when numbers were first being figured out, when we were first coming up with numbers a long, long time ago, we realized that, you know, we like to count up our stuff that we had. Humans like to count up all of our things. And so we came up with these numbers. But then we realized we needed a number that represented having nothing. And so we came up with the number 0. And 0, kind of the numbers progressed. So 0 is our whole numbers, and our whole numbers are kind of like the extended family, right? They include all of the immediate family, all of the natural counting numbers, but then they also include some extra things. If I were talking about my family tree, it would be like my cousins and aunts and uncles. But if I'm talking about the rational number system, the whole numbers include all of the natural numbers, but they also include the number 0, 1, 2, 3, 4, 5, and on and on and on, okay? So the whole numbers are all of the counting numbers plus 0. Well, then humans realized, well, hey, what about people who have less than nothing? What about people who owe stuff, right? We got to have a number to represent that. And so I came up with the negative numbers, -3, -2, -1, and then the integers group includes all the negative whole numbers. It includes all the positive whole numbers, 0, 1, 2, 3, and on and on and on in both directions, right? So the integers are the next level in our family tree, and they include all the negative and positive whole numbers. And we call those the integers. And then the last group that we have, of course, would be the rational numbers. And that's the big game, right? That's what we want to figure out. What are the rational versus the irrational numbers? And so, as number systems were being developed, we realized we needed to have something that represented parts of numbers. And so we came up with fractions. And fractions are parts of numbers. So we include all the integers in the rational number system, but we include all the whole numbers, we include all the counting numbers, all of those are included. That's why all of these boxes are kind of inside each other. They're kind of different layers, and like a family tree, right? So the rational numbers include all of the boxes that are inside it, but they also include fractions or parts of numbers. And so I could also say any decimal number that can be expressed as a fraction. So any decimal number that repeats, so any decimal number that repeats or terminates. And what that means is if I have a decimal number that repeats, like 0.333 repeating, ooh, that was a weird 3. Well, that's a decimal number that I can actually turn back into a fraction. It could also be expressed as the fraction 1/3. If I have a decimal number that terminates, that means it stops. 0.5. There's no other numbers besides zeros after it. And so I can turn that back into a fraction. It represents the fraction 1/2. So any decimal numbers that can be turned back into fractions that represent fractions, and the decimal numbers that represent fractions are decimal numbers that repeat or decimal numbers that just stop, right? Any decimal number that stops, even 1, 2, 5, the way I turn it back into a fraction is I put it over its place value and then I reduce it, right? So I could take my decimal numbers and I can turn them back into fractions, and as long as they're repeaters or decimal numbers that stop at some point, I can turn them back into fractions. So any decimal number that represents a fraction is also rational. Any integer is rational, any whole number is rational, any counting number is rational, and any fraction or decimal that represents a fraction. Okay, so let's classify some numbers really quick. Let's see what we can do. What about the number 0? What groups does the number 0 belong to, right? So let's classify it. Well, if I look here, is it a counting number? Nope, 0 is not a counting number. Is 0 a whole number? Yes, 0 would be classified as a whole number. 0 would also be classified as an integer. And 0 would also be classified as rational. So those are the groups that it belongs to. It would not be classified as a counting number because 0 is not included in that group. Okay, so let's try again. I'm going to put this 0 right out here. We've classified it. I'll put it in with the integers for now. Okay, what about 7/1? Well, 7/1 is equal to the number 7. So 7 would be a counting number or a natural number. It would be a whole number. It would be an integer. And it would be rational. It's all of those things. And because 7/1, right, is the same as or equal to the number 7, it belongs in all of those groups. All right, let's try again. Let's do some more classifying. We're going to put that over here in our rational numbers box. 5/2. Again, it's a fraction. Any fraction is rational. Now, is it a natural number, a counting number? No, it's not that. Is it a whole number? No, it's not that. Is it an integer? Nope, it's not an integer. So the only group that 5/2 belongs to is the rational numbers group. Okay, what about the square root of 10? Well, I'm going to have to put the square root of 10 in my calculator and see, does it come out evenly? Does it come out as a decimal number? What have I got here? So I'm going to put it in my calculator. I'm going to do the square root of 10 in my calculator, and it gives me a big, long decimal number. It says 3.162277766, right? And then because my calculator won't tell me all the rest, that's as far as my calculator can calculate out to. But if you see a number like this in your calculator, that's most likely going to be an irrational number. It's a decimal number that keeps going on and on forever and never stops and never repeats. What about the decimal number 5.26? Does it stop? does it repeat? Well, it doesn't repeat, but it does have an ending point. There's no dots on the end here to indicate that it's going on and on forever. And so I'm just going to classify that as a rational number. It's a decimal number that terminates. Okay, square root of 16. If I stick that in my calculator, it comes out equal to the number 4. So the square root of 16 is, since it's equal to 4, it's going to be a natural number. It's going to be a whole number. It's going to be an integer. And it's going to be rational. So any number that's equal to any of those is all of those groupings. So I can put this in here. I can put it in this box. I could put it in any of these boxes, right? The square root of 16 comes out equal to the number 4, and so it's all of those. Okay, hopefully you can kind of see and you can practice maybe putting some of these others into the categories that they belong to. All right, the last part of our assignment for today is just ordering, putting these numbers in order. And so you're on your assignment today, you're going to be asked to put some numbers in order from least to greatest. Well, if I came and I just talked to you in German, you wouldn't understand what I was saying. Well, maybe some of you would, but some of you would not, because we are not speaking the same language. You speak English and I'm speaking German, and we wouldn't understand each other. And so we have to be speaking in the same language to be able to understand each other. Well, same thing with numbers. If I have a number that's expressed as a fraction or a square root or a decimal, they're all kind of speaking different languages. So the only language that all numbers can speak is decimal. All numbers can speak decimal. They can all be put into a decimal number. And so if I want to be able to put these numbers in order, the best way to do it is put them all in so that they're speaking the same language. Let's convert these to decimals, and then we can kind of compare and see which decimal number is bigger, which one's smaller. So in your calculator right now, you should pause the video and you should put these numbers into decimal numbers. Okay, hopefully you converted these to decimal numbers and you found out that 7/9 was 0.7 repeating, and the square root of 0.49 is 0.7, and then these are already decimal numbers, and so we are going to leave them as decimal numbers. But now I have all these decimals and I can compare which one is bigger. So think in your mind, try and figure out which one is bigger. Whenever I'm comparing decimal numbers, sometimes if I'm looking at these, well, hey, all of these start out with the same decimal number in the 10th place, right? They all have 7s in the 10th place. So it might be hard for me to decide which one is bigger and which one is smaller. And so what I have to do if I want to decide which one's bigger and which one's smaller is I have to look at the next decimal place over. This next decimal place is a 1. This next decimal place is a 7. What would the next decimal place on this number be? What would the next decimal place on this number be? Hopefully, you know that any decimal number that I have, if there's not a decimal place expressed, the next decimal place expressed would be a 0. Hopefully you remember that from elementary school. And if I have a repeating bar on it, the next decimal place, it's going to repeat, right? And so the next decimal place here would be a 7. And so now I can compare the 100th place and see which one is bigger and which one is smaller. And obviously 0 is the smallest number in the 100th place. And so the square root of 0.49 is my smallest number. It's my smallest number. And now I can start to put these numbers in order from least to greatest, right? And that's what I want to do. So the next smallest number would be 0.715. And then I can go from there. The next smallest number, well, crap, because now these both have 7s, right, in my decimal places I was looking at. So I've got to go to the next decimal place? Well, the next decimal place here would be, of course, 0. The next decimal place here would be another 7. And so the next smallest is 0.77. And then finally, the biggest number in the group would be 7/9. And so you're going to kind of be doing something similarly on your homework assignment, where I'm going to give you a group of numbers and you're going to put them in order from least to greatest. And we can use decimal numbers in order to do that. Okay, so let's just really quickly go over a problem that's straight off of your homework assignment. This one's right off your homework assignment, just to give you an example of the types of questions you're going to be asked. And number 1 says, cross out one number which does not belong in the set. Okay, so take a look at this set. It says only whole numbers should belong in this set. So let's take a look. Which one does not belong? You should pause the video and try and answer some of these on your own and see how you do, and then come back. You can check your answers. Okay, hopefully you said the number that's not a whole number, right, is 8.5 because it has a decimal in it. It's got a fraction in it, 8.5, and so it's not a whole number. That's the one that doesn't belong. What about in the integers? Hopefully you said the number that doesn't belong, again, is the fraction, right? Because integers are only positive and negative whole numbers. All right, so some of these you might have to use a process of elimination in order to kind of figure out, okay, wait a minute, what does belong, what doesn't? So when we get to rational numbers, what belongs and what doesn't? Well, are rational numbers whole numbers? Yes, so this one belongs, right? Are they fractions? Yes. Are they decimal numbers that stop? Yes, right? Well, I don't know about this square root thingy, and I might be unsure about this decimal number, but I know that the 100 fits there, right? Okay, and then I have to know something about maybe this decimal number in here. What do I know if it has a bar on it? Well, the bar says that it's repeating. Oh, okay, well, Ms. Miner said any repeating decimal is rational, so I'm going to keep that one. So it comes down to between my square roots, right? So I'm going to put those in my calculator and calculate them out. Look and see what kind of decimal numbers do they have. Are they repeating decimals? Are they decimal numbers that stop? Maybe they're equal to a whole number. And so once I calculate these out, I find out that 81 is, the square root of 81 is equal to 9. 9 is a whole number. The square root of 40 is a non-terminating, non-repeating decimal. So this is the one that doesn't belong in the rational numbers group. And so that's the one I'm gonna cross out. Okay, so that's kind of how we do that. We're going to use our calculators to help us. Okay, let's take a look at number 2. All right, because number 2 can be a little bit tricky. It says I want all 9 integers. So now I have to be thinking in my mind what an integer is. And I want all 9 integers that are between, right? Between negative 3.5 and positive 5.5. So I have to think about, what are integers? Well, integers are positive and negative whole numbers. I don't want any fractions. I just want the positive or negative whole numbers that are between here and here. So I'm kind of thinking in my mind like a number line, or you can draw it on your paper like I did. And then I'm saying, okay, well, what would be too far, right? What whole number would be right here? Or yeah, what negative whole number would be next? If I'm going from negative 3.5, what's the next negative whole number I would get to? Well, it would be negative 4, right? So the whole number that would be above negative 3.5 would be negative 3. And then negative 2, and then negative 1, and then 0, and then 1, and 2, and 3, and 4, and 5, and then 6 would be too far. 6 would be past 5.5. So I need 9 integers that are between negative 3.5 and 5. Well, if I'm looking in between here and here, do I have 9? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep, I've got them all. So my answer is going to be negative 3, negative 2, -1, 0, 1, 2, 3, 4, and 5. Those are the 9 integers that are between there and there. So now you're going to do the same thing, but this time you're only going to want the whole numbers. So you can think about what would a whole number be, and I need 6 whole numbers between -3.5 and 5.5. The last one in this section says something like this. Okay, so I need rational numbers between 3 and 3.9. So rational numbers are any whole number, positive or negative, and any fraction. So I need a fraction or a whole number that's between 3 and 3.9. Well, there's no whole numbers in between there, right? So I've got to come up with a fraction that's in between 3 and 3.9. So try and think of some fractions. There's an unlimited number of fractions that are between 3 and 3.9. You just have to come up with 3, right? So that's kind of how we're doing it. Think about what kinds of numbers fit into that group, and then hopefully that helps you get where you need to go. All right, okay, so that's all that we have for our lesson today. If you have any questions, be sure you're contacting me or Ms. Zeider, and you're welcome to come in and get some help after school, or you're welcome to come chat with us during our Google Meets on Wednesday. Okay, thanks, guys.